aptly absent from the statements of theorem 1.35 is the assertion that the integrals of the sum is the sum of the integrals. This is a fundamental property that any integral should have. The proof that integrals in definitions 1.34 indeed satisfy these crucial conditions requires some preparation. The first step is to verify this property for integrals of step functions. And the second step is the best monotone convergence theorem 1.37. Lemma 1.36. Additivity for step functions. Let X capital A mu be a measurable space and let ST from X to 0 infinity be measurable step functions. We have statement I. For every measurable set E is in capital A, we have the integral on E S of T de mu is equal to the integral on E S de mu plus integral on E T de mu. Statement I. If E1, E2, E3 is a sequence of pairwise disjoint measurable sets, then the integral on E S de mu is equal to the sum of k from 1 to infinity, the integral on ek as the mu, while E is equal to the unions of ek. K is in the set of natural numbers. Now we prove. Right. The function S and T be the form. S is equal to the sum of alpha I, khi I is from 1 to m. And T is equal to the sum of beta j, khi bj, j is from 1 to n. Where alpha I, beta j are in 0 infinitive and ai, bj in capital A such that the intersection between AI and AI as for is the empty sets for I is different from I as for and BJ, the intersection between BJ and BJ as apostrophe is the empty set for J is different from J as apostrophe, and X is contains unions of I is from 1 to n, and it is equal to unions of Bj, J is from 1 to n. Then S plus T is equal to the sum I from 1 to n. The sum J is from 1 to n. Alpha I, beta J, khi the intersection between AI and Bj. And hence, the intersection on E S plus T de mu is equal to the sum I from 1 to n, J from 1 to n, alpha I plus beta J mu, the intersection between AI, Bj, and D. And it is equal to the sum of alpha I is from 1 to n, the sum of J from 1 to n, mu, the intersection between AI, Bj, E, plus the sum of beta J, J from 1 to n, the sum of mu as the intersection between I, Bj, and E is from 1 to n. And it is equal to the integral on E as the mu plus integral on E t d mu. To prove statement I, let's EI, E2, E3 be a sequence of pairwise disjoint measurable sets, and define E is equal to the unions of EK, K is from 1 to infinity. Then the integral on E as the mu is equal to the sum of alpha I mu, the intersection between E and I is from 1 to m, and it's equal to the sum of alpha I is from 1 to m. The sum of mu, the intersection between EK and AI is from 1 to infinity, and it's equal to the sum of alpha I is from 1 to m. Lim n tends to infinity, the sum of mu the intersection between EK and AI, K is from 1 to n, and it's equal to the limits of the sum of alpha I is from 1 to n. The sum of mu is intersection between EK and AI is from 1 to n. Is from 1 to n. And it's equal to lim n tends to infinity. The sum of k from 1 to n. The sum of I from 1 to m. Alpha I mu EK as the intersection between EK and AI. And it's equal to lim the intersection the sum of k from 1 to n is the integral on EK as the mu n tend to infinity, and it's equal to the sum of k from 1 to infinity, the integral on EK as the mu. This proves lemma 1.36.